Hi, welcome to Teardown Tuesday. This is a follow-up to the previous video, which was an unboxing and playing around with the new GW Instek GDS-2000A series VPO oscilloscope. So let's tear it down, see what's inside, including hopefully the logic analyzer modules, if we can take those apart, and definitely the option modules as well for the function gen and the logic analyzer. Let's see what's inside this puppy. Just as a quick aside that I didn't mention in the previous video because I didn't know about it, and you would think that because this has two function generator output B and C's on the front that this is a dual channel function generator. Well, according to the manual, it's not. If you read it, it says if you plug in two of these, you can only use one at any one time. Crazy! Why have two B and C's on the front, and which implies a dual channel function generator, if you can't actually do it? It's insane. Anyway, I don't have a second one to test that, but that's what it says in the manual. So maybe we'll start out with this function generator and see what's inside this. So I can only presume what they're doing there is having a separate B and C output coming from a dedicated pin on this option module, so it doesn't matter which slot you plug this function gen module into, it'll either route it through manually through to the channel 1 B and C or the channel 2 B and C. So they don't have to put like a relay inside to switch the thing. But man, unbelievable. And we've got 4 screws on the bottom here, so we'll whip these out. Self-tappers. And what do we expect in here? Well, is it all of the function generator circuitry? And literally, as I said, the output from one of the pins here goes straight to the B and C, or whether or not there's some extra buffer circuitry inside the scope. I don't know. We haven't opened the scope yet. We won't know, but let's whip this open. And, oh, there we go. Mostly ground plane. It looks like we have a programming, so there's some sort of programmable device in here. Let's have a look. Aha! Actually, one of the first things I noticed here was the fact that this, what I thought was metal shield from the outside, is not actually connected to anything at all. I mean, it's got these little raised bits which come up there and then actually do make contact with the board, but it's actually the solder mask part of the board. Like, there's no exposed solder mask on the bottom side of that to actually make contact there, so I don't, look, nothing. I don't know what the deal is there. That's just, it's just floating. And this backing plate here is actually a powder coated metal. It's not actually plastic. Go figure. Well, it's not an FPGA, it's an Altera Max 2 CPLD in a little thin quad flat pack there. JTAG programming interface, of course. Quite a few. It looks like a parallel sort of bus coming in to that. Not much else really. Not much doing on the bottom side in terms of the connections. There's a few around here, but mostly power seems to be grouped in the middle here. And clearly we have our output down here, so it's on a fixed pin. So that'd be the yeah, I think that there looks like there's probably a driver on here, and it does probably go through directly to the B and C output there. And there's the oscillator for the CPLD. And yeah, there's not much else. So at least with the CPLD, it does have some functionality, but not full. It wouldn't have full arbitrary waveform capability or anything like that, really. So we can see that on the power side of things here, though. It looks like a lot of the regulation is done internally to the scope and it's just powered through here. Look, you can see it coming in here. It's decoupled with that cap through an inductor there, and then it just buggers off through some 4 vias down there over to the bottom side over here to an internal layer. This is obviously a 4-layer board. And then it powers off there. It looks like they've got a little low dropout reg there for something or other, for some local regulation, probably for the Max 2 PLD or something like that. But generally it looks like they're just powered directly from the supplies within the scope. But that's not surprising at all. Well, there's absolutely no surprises on this board at all. Of course, it's going to be a DDS generator, so apart from the Max 2 CPLD, which is just probably working as some sort of interface or glue logic on the board, we have, ta-da, surprise, surprise, an analog devices AD9834, one of the Jelly Bean 75 megahertz DDS generators. I've used those myself. They're quite good. So direct digital synthesis up to 75 megahertz. This thing only goes to like 3 or 5 megahertz. But then we have an old school LM311 there. What else have we got? We've got a AD8000, which is a very high speed 1 gig current feedback op amp. And then we have an what do we got here? An OPA 132 precision FET op amp, op07, another precision op amp down in there. Look at that bodge wire. Ah, man. Anyway, they had to do what they had to do, I guess. They couldn't respin this little board. Wouldn't have cost that much. Really, it's not like respinning the main motherboard for the scope or something like that. Oh, anyway, sorry, another relay in here. Our first relay, quad op amp TL074, just jelly bean stuff happening there. And then our output buffer looks to be an AD8009, which is once again a 1 gig, very high speed to give you a high gain bandwidth product current feedback op amp, used for pulse applications and stuff like that. And there's an output relay to switch it off and on. So yeah, pretty much exactly what I expected. Really, nothing fancy at all. It's bare minimum, but they've actually used analog devices parts in here quite extensively, and they're not the cheapest thing around. So they haven't really skimped on price anyway. But feature set, of course, it's just a DDS generator, which means they can't do ARB waveform capability or anything like that. It's not built in. They certainly could come out with better functionality in the future, whether or not there's any, like, you know, there's no second channel modulation capability, because that would need a second DDS chip. This one only has a single DDS chip, so it's not like they can generate a second signal and then modulate it. You would have to do that using, you know, not a discrete method like this, but using a some sort of ARB capability. And just based on the tracking or lack thereof, there's really only an output from this, so I don't see like any sort of analog input coming in for any sort of optional external modulation capability with like an extra connector on the back panel or something like that. Well, you know, because this is module based, there's nothing to actually stop them, you know, whacking an external modulation, revising this thing and whacking an external modulation input on there, for example. So it can certainly be done. They just, you know, have to release a new module that has that capability. Onto the logic analyzer module here, the input module. I don't see any screws on there, so whether or not that's heat sealed or whether or not it's snap sealed, I don't know. I might try and prise it open, but apologies if I can't get that input pod open. I certainly don't want to destroy it. I'd expect there to be a little something in this, because it can certainly detect that it's plugged in, but that could be as simple as, you know, shorting a pin on the connector in there. Could be as simple as that as far as module detection goes. So whether or not there's actually anything in there, we can find out, because, ta-da, this one has screws. Alright, this one just pops open, a little bit of a clip on the side, and wah, 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 wah. Just a cable. And there's nothing on the flip side of that either. Just got the individual pairs running. This is for obviously the 16 channel. That's the extra connector up there for the 16 channel, which isn't populated. Exactly the same pod, but they've only got the one connector wired in. But there you go, it's just got some power wired through there, the thicker traces, and then the individual pairs running back. Interestingly, if you count the pairs, 1, 2, 3, 4, 5, 6, 7, 8, you'll notice that there's an extra pair over here. There's actually 9 pairs for each pod there, and they've got exactly the same on the back, 8 plus that 9th pair. So whether or not that's for an external clock or whatever, I don't know, because it doesn't have an external clock capability on the input here. And the thing with that is, no external clock means no state analysis capability, because logic analyzers have 2 types of mode, either state analysis or timing analysis. And in this case, state analysis requires an external clock so that your sampling of your input signals can be in synchronization with the external clock from your circuit under test. This one doesn't have it. Ta-da! We're into the main pod, which connects to the head. There we go. It looks like, yeah, looks like we have some sort of E squared prom there. We'll take a look at that. And there's some power, definitely some power coming through there. we'll have a look what's on the top. And that is indeed a serial EEPROM, so presumably that is the ID, which then tells the firmware that this module is plugged in. So you can't just make your own pod, you'd have to actually copy that firmware. And of course there's no onboard regulation here, just a couple of inductors there, bit of filtering powered from the main machine, the motherboard on the main machine, and there's the input circuitry, it looks like. Although you can see the traces on the bottom side there going all the way through to the connector, it just doesn't seem to make sense with all that sort of stuff down there. That looks like a lot of that looks like chip bypassing some of that anyway. So I think we're going to find some circuitry underneath this puppy. And that one there, that bunch of those passives there, they indicate that there's active circuitry under there somewhere doing something. And likewise this one down here. So I think we're going to find some chippies under here and here and here. Let's flip it over. Ta-da! Look at that. There we go. We've got some serious logic analyzer stuff happening here. I'm really going to have to get in there with the zoom and have a look at the chip numbers on these interesting looking LCC, or are they little quad? Looks like they're little quad flat packs there. Going to have to get a look in there. Obviously handling 2 channels a pop, and that's why we saw a differential pair coming out possibly. Are they a differential driver? We'll have to have a look. But there's an OPA 177 there, and I'm not sure what that one is. Can't read it. Let's get in there. But it looks like, oh, D diode. It is a diode. That's a funny looking diode package. Wow, look at that. G13 number 119. Obviously doesn't ring any bells off the top of my head. I'm going to have to go Google that one, but I'm not sure if we'll get any luck there. But anyway, look, you can see the individual pixels on the silk screen there. Check it out. You can see that this is a dot printed silk screen. Pretty cheap and nasty one, geez, but not that it matters. Just thought I'd point it out. But anyway, I've got 4 of those, clearly handling 2 channels each. And that one there, LBMHN 891225, I don't know, obviously some sort of DC to DC converter locally. I'm not sure why. Geez, does it need that much power right at the head to drive these logic analyzer input buffers here? I don't know. Well, I don't know about that G13. I couldn't immediately find anything on Google. There's like a Renesas RL78 G13 micro, but that's definitely not it. This is only a 16-pin package. It's not going to be a microcontroller there, so I don't know. If you got any info on that, please leave it in the comments or on the EEVblog forum. And there's our input network there, coming directly from the connector. Small value series resistor there, 90 odd K resistor there. So there you have it. I'm quite impressed by that. The build quality's excellent, and design quality looks good, and you do actually get a decent logic analyzer input for your money anyway, for what, your $500 for the logic analyzer option. And of course their input logic threshold as well. I don't know where that's set. Clearly that's it could be going into these devices. They could be, you know, fully programmable input, programmable thresholds and stuff like that. So that could actually be quite a little complex beast on the input there. And once again, I'm not going to spend a lot of time trying to track down the info on that. I'll leave it up to the viewer. Someone will post it. Now let's do what everyone's come here to see, the main scope. Looks like we have some maybe self-tappers down here, I don't know, and a couple up the top here, but yep, there we go. Let me zoom out a bit. A couple up the top here under the handle, and that's all she wrote. So as I said in the previous video, I expect this to be quite decent quality. GW Instek are quite a reputable company. Metal threaded inserts, of course, so the other ones are obviously that. I would have been disappointed if they were self-tappers. And, oh, dropped it. always have leftover screws, or not enough when you put it back together. Ah well. So anyway, the back cover will just lift off. I don't see much screen. Oh yeah, there's probably looks like there's a big metal shield inside. So we expect that in modern scopes. EMI is a big issue, so they have to knock that on the head pretty well. So it looks like this will just pop off. I can see our noisy fan in there. Oh, there we go. Too easy. Ta-da! But it looks like, no, oh yeah, there we go. Separate power supply there on its own board, not shielded in its own right, which is a lot different to some of the other scopes modern scopes I've taken apart. Usually this is or in its own, the power supply is in its own shielded enclosure, but no, there it is, just hanging its ass in the breeze there. So that's not terribly exciting. If you don't like the noisy fan, you could get in there and replace that. Not a problem. They've got a separate output board here, which we'll take a look at for the USB and the serial and the other BNCs going via cable. It's all neatly cable tied. Not a problem. We've got our slots coming out here, our PCI slots, and well, looks pretty simple, but nothing wrong so far, really. Bit disappointed though that there's not a shield on that. Actually, one thing that just became immediately obvious where I really haven't seen this before, where are the output voltage cables on these? Usually you see nice big beefy, you know, individually wide output cables, big Molex connector, something like that, nice high current, things like that. No, all we've got is a bloody standard 0.1 inch ribbon cable. Are you kidding me? That's the entire output supply from this thing going over to the main board. What? How much power does this thing take? It can't take much, or either that or they're really pushing the margins there with a little... Well, they're probably using multiple pins, of course, but, you know, there's generally, rule of thumb with these, there's only an amp per pin or thereabouts. But, yeah, geez, a 0.1 inch header? Give me a break. Now this is interesting. Check out this. They've just got like an afterthought almost. Oh, let's just bring this winding out here. We don't have enough pins on our the bottom of the thing. Let's just bring out an individual winding and put it in there. And yeah, okay, they've glued it down. That's okay. But geez, you know, almost like an afterthought. They've glued that resistor in there. A little bit of attention to detail just to ensure that it doesn't flap around in the breeze. They've got some input protection down there. I see a MOV and a thermistor down there. Fuse, of course. It's not directly soldered in. Why they've got this just jumping over to there like that, I don't know. Maybe it allows them to get a current clamp over that thing. Perhaps. I don't know. Weird. Anyway, it looks like we do have a common mode choke here, filtering. So they're at least doing all the basic filtering stuff. There's our big ass clunking mechanical switch there. Very nice. I like that. It doesn't look like they're faking that and just doing standby power. You can see the opto couplers down in there. It's, you know, it looks like a pretty basic, reasonably designed power supply. Let's take a look at the brand of the caps. That, folks, is a Nippon Chemicon symbol. I didn't expect a Nippon Chemicon in here. Excellent. Top world-class brand cap in there. I assume it looks like all of them, even the output caps over here, Nippon Chemicon. Brilliant. Every single one of them. They haven't used another brand electro in there. Very nice. I'm impressed. Thumbs up. And they're the KMG series for those playing along at home. 105 degrees C. They got that a tad close to the almost touching the heatsink down in there. That's not great for longevity. Once again, another one right next to the heatsink. But, you know, these things, you are cramped for space. But, you know, that one over there, there's probably no excuse for putting, like, almost touching that heatsink, really. But anyway, I'm impressed with the quality of the caps. That's for sure. Usually you'll get a mix of brands of caps in this thing, but in a typical power supply, they'll skimp on the ones that aren't super critical to the design. They'll skimp on a cheaper brand to save a few cents here and there to trim off the BOM cost. But no, they've used Nippon Chemicon throughout. And there's nothing worth looking at on this USB and RS-232 connector board up here, but you'll notice the nice little RFI EMI fingers there on the connectors. Nice, they've done that right. Now it's interesting to note, when you look at the side profile of this thing, you'll see all the circuitry is within half the depth of this thing. The other half is taken up with the power supply in this horizontal configuration like this, and the fan, which is then, mounted out like that, and this connector board on the back. If they really wanted to, put some engineering effort into it, they could have actually made it not much thicker than that itself. But then again, it almost becomes pointless because, well, how do you can make something that thin for sure, but then how do you keep it from, falling over and stuff like that? You've got to have proper, tilt feet like that come out to give it some counter balance on there and that sort of stuff. So, but interesting to note, they could have done that. And ta-da, I popped that whole metal shield off and we're in like Flynn. Look at that. One main board, of course. No surprises. I sense an Analog Devices Blackfin DSP up here. We've seen those before in the Rygold. Some heatsink stuck onto... Oh, I could almost move that, but I won't take... Oh, should I try and get those heatsinks off to have a look at the chip? I don't know. I probably shouldn't. Oh, geez, but look, looks like we can get through the metal shield here for our 4 channels. This is marked as the 4-channel board. Of course, the 2-channel board, presumably, the 2-channel scope wouldn't have complete 2 channels populated in here, and probably that second device here, because as you saw in the second video, the sample rate does halve when you turn on channel 1 and channel 2, for example. The sample rate halves. So obviously they've got the 1 chip controlling the 2 channels, the second device over here. So that's why if you turn on channel 1 and channel 3, the sample rate doesn't halve, because you've got a separate chip handling each one. But presumably they wouldn't be silly enough to populate all those if you're only buying the 2-channel model, because it's not software upgradable or license upgradable or anything like that. You're physically paying more for the extra 2-channel front end, probably the extra chip there and maybe something else, but that's the main cost. But there you go. It's pretty Spartan, actually. I like it. Let's have a look at the main devices. All right, 3 devices here. Analog Devices Blackfin DSP, ADSP, BF531. We've seen these it's used pretty frequently in these scopes, actually. So, yeah, it seems to be the processor of choice for driving, the GUI interface of these scopes. Of course, it doesn't handle, the input sampling and processing and all that sort of stuff. It's just pretty much the, the operating system, the on-screen graphics and user interface and things like that. Then we've got an ISP1761 USB host controller, and also an Altera Max2 CPLD, same as what we saw in the module there. And then no surprise to find that that CPLD is actually hooked up to the modules there. So obviously some sort of glue logic that handles the module function capability, something like that. And coupled around what's clearly an FPGA under here. I don't know if I'll remove that heatsink yet. Could be really messy, I don't know. But anyway, we've got ourselves a GS88036 CGT, a 9 megabit synchronous SRAM in a 256K times 36-bit configuration. So effectively a total there of only 2 megabytes, but that's what this thing's got, 2 megabytes of sample memory. So clearly that's 2 mega sample memory with an extra bit. And of course, coupled onto our FPGA, these 2 suckers under here are obviously our analog to digital converters. Dead giveaway, because they're right near the vertical front ends. The vertical front ends straight out of the programmable gain amp there, straight up into the dual analog to digital converters. As I said, if you bought the 2-channel module, you'd probably only get the 1 ADC. And curiously, next to that, there is a metal can. Check that out. And that one's actually soldered directly onto the board. What a bastard. I'm definitely not going to desolder that can to see what's under there, but I don't know. Is that like a ADC clock or something, perhaps? I don't know. let's have a look at that puppy in there. Looks a bit interesting. And no surprises, defined and ultra-fast comparator analog devices AD-CMP567. Obviously used for part of the triggering circuitry. And ta-da! I popped the heatsink on it, and here it is. They haven't scrubbed the numbers off. Brilliant. The ADC is a National Semiconductor, now TI, ADC 8D500, which is a 500 meg sample per second 8-bit dual analog to digital converter. So basically, one of these converters is only capable of either 500 meg samples per second on dual channel or one channel at 1 gig sample per second if you interleave them. Now, of course, this is a 2 gig sample per second scope. So maybe the 2-channel version actually does populate both analog to digital converters, and that's how they get, using 4 of those converters in 2 chips, that's how they get the 2 gig sample per second. Either that or they're overclocking. And I popped the skirt on the main chip there, and of course, yes, I was right, it is an FPGA off-the-shelf Altera Cyclone for the EP4CE30F29 blah blah blah. Go look it up if you want to know the exact gate count and feature set. Now here's the interesting thing, or possibly not so interesting thing, depending on how you look at it. Compared to the Rigol and the Agilent teardowns that were seen in the past, for example, modern scopes, this one, yeah, we've got our ADCs here, we've got our one FPGA here, pretty good FPGA in it, but it's only one. So presumably, this is only doing the sampling, all that sort of stuff, and the trigger and everything else, plus probably, you know, the intensity grading, color mapping and all that sort of jazz as well. But look where the LCD is connected. It looks like it's right next to, coupled to, the analog device's black fin DSP. Now, if I can't see where the traces on there go, they could actually go down here to the FPGA. In that case, okay, they're mapping the data directly from the FPGA onto the screen, and that's how they're able to get 80,000 waveform updates per second. But if they're not, then they're driving it from the Blackfin DSP, and that's going to be a big bottleneck, and that's probably why the intensity grading isn't that great. But anyway, I'm not going to make a call until I flip it over and see where those pairs are going. So they could go over to here. I see a couple of traces, see a bunch of traces in there that could jump over, but more likely I think it's due to the placement. But then again, I don't know. Let's flip it over. But anyway, that's different to the Rigol one, which of course has a dedicated display FPGA. Better horsepower, and that's how it can get like its multi 256 level intensity graded display or whatever it is. Whereas this one, who knows, they might be doing it in and taxing that poor old Blackfin processor. And to get the main board out, unfortunately, we do have to lift out the entire, or take off the front panel with the rubber key mattings and everything else. So, well, I'll put those back into place soon. Where'd they come from? There we go. Ta-da! Not a problem. There we go. That's our front of our board. There's the top key mapping. Nothing exciting on the top here. I won't even bother like unscrewing all of the top board here and the LCD. Not very exciting. I just want to take a look at the underside of that board. And we've got the LCD cable hooked on, but there we go. We've got some more memory on the bottom. Aha. Yep, duplicated memory on the bottom there. So we've actually got double the amount of memory that I said before. It looks like exactly the same devices that we had on the top. So yep, doubled our amount of memory. We've got our program flash down here, and that's all it is. That's all she wrote. And there's those vias for the LCD there. That's the LCD cable. Goes up to a separate board in there. Not much doing there at all. It's just got a little bit of a is that like a backlight inverter or something on there? I don't know. But yeah, nothing interesting. But I can't see where those traces go, whether or not they come down here to the main FPGA. It doesn't look like they do. I think they've got to be coupled into that DSP. So my money would be on the Blackfin DSP handling all of the display processing, and that's a bottleneck compared to the Agilent one, which does it in the MegaZoom 4 ASIC, and compared to the Rigol 2000, which does it in a dedicated FPGA. But you know what, if that's actually the case, then getting, you know, the 80,000 waveform updates per second via that Blackfin DSP is actually quite impressive. And on the back side of the input amplifiers here, we've got a reasonable amount of heatsink, well, you know, a bottom ground plane heatsink. You can see all the via stitching there going from the back of the device, thermal pad on the back of the device there. That'd be like the output amp, which is driving the ADC, which are around about here somewhere. And that, because that's the top part, that'd be the final output differential driver to drive the ADC differentially. Not much on the bottom of the front end here. The front end's very unexciting. They've got some solder masks removed in various spots here where they, you know, because this is like a 300 megahertz bandwidth front end, then yeah, they've just removed some ground plane on the top there just to get the performance they need. But apart from that, nothing else interesting on here, apart from all the decoupling on that FPGA. So there you go, folks. If you want to know what sort of decoupling is required on the bottom of something like that Spartan 6 FPGA in there, pretty big beast then. Yeah, look at all that little bastard 0402 parts in there. But yeah, you have to do that to fit them in. But that is the sort of decoupling you require. And of course, this would be like a 6 or 8 layer board in order to fan out all of the signals. You can see all the vias in there. There's lots of decouplers, you know, solid decoupling in the middle in there. But some of these vias have to get all the way out past all these other ones, because you can only run 1 or maybe 2 if you're lucky traces between each pad. So you've got to have all those different layers to route out all the signals. And of course, the soldering is first class on this. Can't find any problems at all. No leftover residue or anything like that. Both top and bottom side of the board. And for those curious to see how they handle big thermal mass items like the front panel B and C there, those solder joints, yeah, look cold and frosty, but that's the lead-free stuff for you. There's absolutely nothing wrong with that at all. And speaking of the front end, I'm sure we have a lot of people very interested in the design of this 300 megahertz front end, because yes, it'll be the same design from the 70 megahertz model upwards. And if you want to check out the high-res photos of this board, hop on over to my Flickr account. The link is always in my description below. That's where I post, usually post high-res photos of my teardown. So I'm sure there'll be no shortage of people sort of reverse engineering this front end as well. You don't have to reverse engineer it, you know, it's pretty easy because they haven't rubbed off any numbers at all here. But there we go. We've just got some input coupling there. On the input, we've got a relay. We've got 2 relays. Looks like we've got a solid state relay. We've got a trimmer cap. We've got another trimmer cap. Further up, we've got a second relay there, and a few passives. And there's a few transistors in there as well, discretes, and all that leads up to, ta-da, that would be our output programmable gain amp and ADC driver. That's the one that's actually heat sunk, so that'll have a thermal pad on the bottom of that, which then goes through to the exposed copper on the other side to try and keep the heat down on that. I'll see if I can get the part number. I see it's a National Semiconductor. And yet, National Semiconductor VM21AB. This shows that you really have to get the angle on this to really read these suckers. You just got to get the right contrast. There it is. Let me go look that up. And aha, that's actually the LMH6518, and no surprises whatsoever, it is the recommended device for that particular National Semiconductor analog to digital converter, designed, almost, you know, very, well, listed one of the applications for an oscilloscope front end. Go figure. And that's actually a 900 megahertz programmable gain amp, and yes, it does have via SPI, the gain's controllable via SPI, and yes, it does have internal bandwidth limiters on the output of I think 60, 100, 200, and then 350 megahertz. So they're probably using that as the bandwidth limiter, although I wouldn't rule out that they've got something else down in there that they could switch with a digital line or something like that to do the filtering. So yeah, I don't know. Someone will no doubt reverse end, I don't see a varactor in there or anything like that. There certainly could be. I don't know. I'm not going to decode it. I'll leave that up to the aficionados out there to tell us exactly how their software bandwidth limiting this thing. And but yeah, there's definitely the capability built into that device directly on the output. So if they are actually using this chip as the bandwidth limiter for the different models, then yes, in theory you could get in there, tap into the SPI line, and then change the command to increase the output bandwidth of that ADC driver amp. But who knows, they may actually, because this thing is not software upgradable, they may actually choose different parts in there, for example, so there could be different resistor or capacitor values or something like that to actually bandwidth limit that somewhere else. But then that wouldn't leave their options open for the future if they wanted to then offer a bandwidth upgradable model. So yeah, anyway, in theory, you could actually crack into the SPI bus on that and change the gain to anything you like. But of course, then you wouldn't have things like the time-based setting and other stuff in the software. So yeah, I don't know. I'll leave that one definitely up to the aficionados. Now, interestingly, if you look at the membrane, key membrane on the front panel, there's 3 more buttons down in here, and it's like, aha, is there, some upgrade or some potential future upgrade? Well, let's lift that up and have a look. It looks like it's just duplicated. Look, math, ref, bus. Yeah, for those curious to see what the rotary encoders are, well, they're 124A1. I have no idea. There's no brand marked on there at all. So, of course, these things get wear and tear. They are something that could potentially or almost certainly will eventually wear out in some people's machines. Depends on how often you use them. So, if anyone has any more details on that, post it. And for those curious to see the trigger circuitry in here, well, I'll post the high-res photos. I won't go into details here, but if anyone wants to, any of your trigger aficionados there want to check it out, by all means do. Aha, there's the same AD CMP567 we saw further up on the board, and that's that ultra-fast comparator. So there you have it. That's a teardown of the new GW Instek GDS-2000A series oscilloscope, and thanks to GW Instek for sending that in. Most interesting build quality, yeah, first class as you'd expect, like from a company like GW Instek. They're not one of the one hung low cheapies, that's for sure. So build, solder quality, design quality, very well done. I like it. No problems whatsoever. Just a bit, maybe, just a bit underpowered, say, compared to the Rigol 2000 series, for example, or the Agilent 2000 series as well with their Mega Zoom 4 ASIC. So, yeah, only the single FPGA. I was a bit surprised by that. I was expecting to see a second one, but I guess I still don't know whether or not the display is directly driven from the Analog Devices Blackfin or the FPGA. I'll have to figure that out, or if somebody can come through with more info, then please do exactly how they're doing that. But anyway, that was an interesting teardown, as it always is with these test equipment. I really like them, and as I said before, if you want to see the high-res photos of this, jump on over to my Flickr account. The link will be down below, and there'll, I'm sure, be no shortage of people discussing this on the EEVblog forum. So, if you like Teardown Tuesday, please give it a big thumbs up. I'm working late tonight, 7:30. Well, that's late for a family man. You know, catch you next time.